Okay, so hello and welcome back. So the next question that we have here is question number 17. Question number 17, which is let A be a non-singular square matrix. Let A be a non-singular square matrix of order 3 by 3. Then basically the determinant of adjoint A is equal to choice A, the determinant A, choice B, the determinant A whole square, choice C is determinant A whole cube, and choice D 3 times determinant A. Now I try to, what you can do is that actually what I was doing was that I was trying to do this on an actual matrix and see what I would get. But it seems that there is actually a better solution, and I suspected that there would be another solution, and I took a look at the solutions, and I saw that basically we had this relationship between the adjoint A and A. We basically previously showed that the adjoint of A times A is equal to A times the adjoint of A is equal to determinant A times I, right? So the adjoint of A is of course a matrix, and this is a matrix, and these two are matrices, and this is a matrix. This is a determinant, which is just a number, right? Now you can say that based on this relationship, you can say that basically the adjoint of A, you can say that the adjoint of A times A is equal to the determinant A times I, right? I'm not writing this part. And then I can write basically the adjoint of A times A is equal to basically the determinant A times I, which is basically a matrix of order 3, for example, let's say, because our matrix here is of order 3, so 0, 1, 0, 0, 0, 1. And therefore we have basically now since I want to know what happens to the adjoint of A, to the determinant of adjoint of A, I will take the determinant of both sides of this equation, meaning that I will write the adjoint of A times A and take the determinant of that is equal to basically the determinant of A times the determinant of this matrix, meaning that I write the determinant A times instead of a matrix I write the determinant 0, 1, 1, 0, 0, 0, 1, 0, and 0, 1, 0, 0, 1. And the reason why you can do this is that basically you can of course write this as this part, you can write it as this matrix as determinant A 0, 0, and then 0 determinant A, for example 0, 0, 0 determinant A, and then as a matrix. And if I take then the determinant of this matrix, then I would get just simply a determinant like this, and then from this determinant I can take basically I can take the determinant of A from each row out, meaning that I would be able to write the determinant A times the determinant A times the determinant A times this determinant, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you know that the value of this determinant is 1, right? So this doesn't have just a 1. And this would be determinant A whole cube. That means that if I write the determinant of adjoint A times A, that I could actually write it as the determinant A whole cube. Now, what we saw before was that there was a relationship between determinants. We said that basically the determinant of A times B, if I'm not mistaken, let me take a look at there was in one of those theorems, we said that so we said that basically theorem number 3, we said that basically determinant AB is the same thing as determinant A times determinant B, right? So we can do this, meaning that I can write this as the determinant of adjoint of A times the determinant A is equal to determinant A whole cube, and then I can divide both sides of this equation by determinant A. I would get basically the determinant of adjoint A is equal to determinant of A whole squared, which is basically the choice B here, and therefore choice B is the correct answer. So you need to be careful, for example, when you want to do operations on these determinants and matrices. It's not like simple algebra, and of course when it comes to determinants and matrices, they are in many ways, in many cases, different. So we have to be careful about that. So that is basically that. So therefore what we learn here is that if A is a non-singular square matrix of, meaning that the determinant of the matrix A is not equal to 0, and if it's of order 3, then basically the determinant of adjoint A is equal to determinant A whole squared. But of course you can find what that would be in general, for example, in terms of the order of the matrices, but we don't have it here, and so that was the question that we were supposed to answer. Now, question number 18 is, if A is an invertible matrix of order 2, if A is an invertible matrix of order 2, then determinant A inverse, is equal to, so you have choice A, determinant A, you have choice B, 1 over determinant A, choice C you have 1, and choice D you have 0. Okay, so now the way to answer this question, so we know that basically A is an invertible matrix. If basically we had a basically theorem here, so you can, of course, you would remember that, you do remember that we said that in theorem number 4, we said that a square matrix A is invertible if and only if it's non-singular matrix, meaning that basically it has to be a non-singular matrix, meaning that the determinant A has to be not equal to 0 so that it is invertible. And vice versa. That means that if your matrix is invertible, that implies that it's non-singular. If it's non-singular, that implies that it's invertible, right? Now here, if A is an invertible matrix of order 2, which implies that it's non-singular, then that means that determinant A is not equal to 0, which means that this would be defined, of course. And because determinant A is in the denominator, and therefore the way to answer this question so you can use the relationship that we had between the determinant A and the inverse of A. We said that the inverse of A is equal to 1 over determinant A times basically times the adjoint of A. You do remember that, of course. So here the order is 2. So basically you can say that the order of the matrix is 2. Hence, so let's basically A be equal to, for example, ABCD, for example. ABCD. Therefore, the determinant A is equal to basically AD minus BC. And basically adjoint of A is equal to this matrix. Along the diagonal you have to switch these two elements, so you get and basically for these two elements you have to change the sign, so you get negative B here, negative C here, and that would be the adjoint of A, right? So I think we can put all of these in here and see what happens. Meaning that I can write the A inverse is equal to 1 over determinant A adjoint of A, and therefore A inverse is equal to 1 over determinant A times the adjoint of A, which is basically this matrix, D negative B, negative C, and A, and which is the same thing as which is the same thing as basically d over basically the determinant A, negative b over determinant A, and negative c over determinant A, and A over determinant A, and A over determinant A. That is A inverse. Now you can say that determinant A inverse, if I take the determinant of this and determinant of this part as well, you can say that the determinant of A inverse is equal to the determinant of this, which you would write the same thing, only the matrix becomes a determinant, so D divided by determinant A, negative B over determinant A, and negative C over determinant A, and A over determinant A, and that becomes a determinant. Okay, so now from this determinant, if I take 1 by basically determinant A out from this row and from this row, I will get 1 by determinant A and times 1 by determinant A. I can take these two out from these two rows and write this as this determinant as D, negative B, negative C and A, which is the same thing as 1 over determinant A whole squared times the determinant D, negative B, negative C and A. Now D, negative B, negative C and A is basically, this is basically the determinant of the, this is the this determinant is the you can write it as determinant of the adjoint of A, determinant of the adjoint of A, right? So actually, if you, maybe I'm wrong, but if I'm not, let me see. The adjoint A is D, negative BCA. That was correct. But then you can write this as, of course you can write this as AD plus minus BC. You can write this as basically 1 over determinant A whole squared times, for example, AD minus BC. That you can write. Now, AD minus BC is actually equal to the determinant of A, because if A is basically, if A is this is A, AD minus BC is actually, so based on what we have here, we can say that determinant A is equal to AD minus BC, right? Is equal to AD minus BC. So AD minus BC, I can write it as 1 over determinant A whole squared times the determinant of A, and then you can cancel out right here determinant A, and it's 1 over determinant A. And therefore the option, the choice B is the correct answer. It's sometimes not really, Actually, if you're looking for something, you will see it. But then, of course, there is many different options that you can consider. Okay, so that was question number 18. Now the next thing that we have here is applications of determinants and matrices. We have about some pages left from this chapter, but it's all about now just application of these determinants in systems of equations, and then the whole thing is over. So now in the next video we will talk about these applications. So I'll see you in the next video, and thank you.